know when you've hit it?
It's recording.
All right, cool. Let's hope, hopefully your computer can take care of the processing there. So this is what the presentation is, what we call the Hit the Ground Running program. So I've started, training a number of BDMs over the several years I've been here. And I kind of came up with this number of presentations to hit each of our product lines just at the core to kind of have a good understanding of the parts and pieces, so the components, the different flavors or styles of bar and styles of lead sections and terminations, and then installation. So all of the things that go into getting an element from above ground into the ground, and then design. For helical piles, the Chance Design Manual is one of the things that we utilize for our designs, and it has a very in-depth, probably too in-depth level of communication for how these things are designed. And you're talking about shear. I don't think it touches on shear too much, so we can discuss that when we get to that point. But if you wanted to get, if you don't have the Chance Design Manual, let me know and I'll get you a copy. We're currently in the 4th edition, which I think was 2019. So if you don't have that, let me know. But basically,
I think we went on and downloaded the recent.
Oh, okay, good. So I'm going to go through it in this order with the kind of background and applications. Then I'm going to go into the components and the different options of all the components. Then I'm going to go into how it's installed, and then I'm going to go into how it's designed. So a helical pier, in a nutshell, is a shaft with flights that screws into the ground, and it gets connected in some way to an existing or a new building or structure. And it's taking the loads from that shallow foundation level, transferring it down into something that's deeper and stiffer or denser, depending on the soil type. You can call them screw piles, helical anchors, it's all the same thing. And they're used for transferring those vertical loads from an existing building or new building through something soft to something competent. You can also use them to hold back retaining walls and basement walls, and depending on your application and level of lateral load, it can also help to provide lateral resistance. And you can do that with vertical piles. We have the round shafts that have the section to be able to resist that lateral load and that flexural moment, or doing a combination of vertical and battered tiebacks, you can actually try and create a static pile cap condition to where those vertical piles won't ever really see the load because they'll never strain enough. So it's important to have an understanding of all that when you're doing the full structure design and understand how it's going to react. So every helical pile has, at a minimum, at least one bearing plate or flight, a central shaft, and a termination. And so that bearing flight takes that load and transfers it into a wider area to decrease the contact pressure with the soil. And so there are multiple options for a lead section, which I'll get into in a moment, but the section that has the flights, if you have more flights, you'll decrease that contact area even more. And that's the balancing point that we're trying to achieve for geotechnical capacity, is distribute that load wide enough to where the soils at that point won't fail in a geotechnical bearing capacity failure. And so that plate area also has an effect on the installation torque. So more plates that you have, the more it's going to drag on the soils and the more torque you're going to generate. So there's also a balancing point of being able to twist everything through soils. So then the central shaft, we have multiple shaft options, and you usually choose those based on your load and soil conditions. And that shaft option transfers the loads axially into the plates at depth. and it also needs to be able to be sized to resist the torque during installation. I'll get into that a little more in the design phase as well. So then you have your termination, and that's the point at which the pile gets connected to the structure, whether it's existing or retrofit. There's a number of termination styles. We also have styles that have a threaded bar at the end of it, eyelets, kind of tie back, hold down applications where you can take cables and things like that and connect it to it. And we also have what's called saddle brackets to connect to wood trusses or columns. And they just sort of kind of come up on the sides of the beams. I have pictures of those later on in the presentation as well. So similar as before, there are three main kind of things we call out for every helical pier. We call out the termination, we call out the extensions, and we call out the lead section. And so I'm going to cover both new construction and retrofit for this presentation. So kind of broken out here, you can see the termination is at the top. This one shows a new construction cap. So that's just a tube with the plate welded on top. And it should be sized such that it can withstand the load transfer from the pile cap into the shaft without having any buckling failures up near the top, and also has enough flexural rigidity and area to not overstress the pile cap as well. The extension sections are just unflighted portions of the bar. Usually these are 3 foot, 5 foot, 7 foot sections, and they're just used to extend your pile deeper as you install because it's a top-down installation method. And then the bottom represents the lead section, and that is the bar section that has the flights on it. And they come in different flavors as well. So then at the top, this is a typical retrofit bracket or an underpinning bracket that you could connect to an existing structure. I'll get into the installation and what that really entails, but basically you're installing this up to the wall, for instance, of an existing building. You try to get this bracket as close to the load as you can to reduce the amount of eccentricity. So a lot of times we'll see people initially, they'll have their spread footing, for instance, and they'll try to put this underfooting bracket on the extent of the edge of that spread footing. But depending on the rigidity of that spread footing, it might not be able to span the load from this column out to the edge of the spread footing. So typically what we recommend is break the footing up to where the load is and try and get this underfooter bracket as close to the load as possible. So I'm going to go into the lead sections in more detail now. So the lead section is the first flighted section of the pier. This is the section that you start installing with. Lead sections are named for their flighted configuration. There will be a bar name, and then it'll be some type of 3 number, 2 number, even 4 or 5 number designation. And what that designation is indicating is the size, the diameter size of the plates on the lead section. So if somebody says an 8, 10, 12, that means that there's an 8-inch plate followed by a 10-inch plate followed by a 12-inch plate. And those plates are spaced such that the stress bulbs implied by those plates won't overlap each other. So you don't have to worry about multiple modes of potential failure between the two, because those bulbs are going to be at most 2B below the plates. We have common lead sections, and then we have lead sections that are maybe a little less common. So it can be important to make sure that if you have a project where you're going to specify or design something, it can be a good idea to check with Bill or whomever you're interacting with on a project to just say, hey, you know, is this lead section a common one? Because sometimes in the product catalogs, there will be things that are kind of uncommon. People don't buy them. There's long lead times. And that's one of the places where we can come and help is establishing a lead section that makes sense on a project early on to where there's no hiccups come project installation time. So that's a benefit that we can provide. And the more plate area, the more torque you can generate, and also the more plate area, the more you can dissipate that load into a lower contact bearing pressure. So you're able to get into a softer soil and not fail it, basically. Also, there is a bolt hole at the top of the shaft, and that's for adding your next extension once you've installed this most of the way into the ground. So after the lead section is twisted into the ground, you add extensions to keep advancing the pile. Extension sections are typically the same shaft material as the lead section, and I'll get into that typically in the special types of piles in a minute. So for the majority of the length of extensions, they won't have flights at all, and they're just used for advancing it. And one of the things that we can do is, if the soils aren't ever dense or stiff, you can have extensions that have plates on them. So we typically have 3 to 4 foot section extensions that have 1 to 2 14-inch diameter plates. And you typically want to have about 5 or 6 at the max for the total flights that you add to a vertical pier. So you might start out on this last slide, you might start out with an 8, 10, 12, and then have a 14, 14 on your pile. So your full pile length will have 8, 10, 12, 14, 14. And so that increase in area decreases your contact pressure and allows you to be in a softer soil than you originally planned for. So after the lead sections in the ground, we added extensions. Like I said before, typical extensions as well as lead sections are 3 foot, 5 foot, 7 foot, or even 10 foot long. You can get longer extensions, and they're more efficient, to install most of the time, but they can get really heavy, and at a certain point, you won't be able to handle them by hand, and you'd have to, rent or have some sort of material handling equipment. So there's, some balancing point between using more smaller piles versus fewer larger piles. And the extensions have a female coupling that sleeves over the male section of the lead section or the previous extension section that's in the ground. So basically, screw the pile all the way into the ground, and you got a little male end sticking up out of the ground. You take your next extension and put the female end onto the male end, bolt them together, and continue screwing your pile into the ground. And I think it'll make sense whenever we get to the visual demonstration of the installation. So new construction termination, went into it a little bit before. The plate, they're just plates with a welded pipe sleeve that go on the last extension that's cut off at the right height. So you just cut off your pile and sleeve this on, and if there's an uplift portion of the pile or tension portion of the pile, you put a bolt through the hole, and that bolt goes through the shaft of the pile. They're sized based on the flexural strength required for the loads and the pile cap so that it doesn't overstress the pile cap. And once the pile has achieved enough torque depth, these are placed on top of the remaining pile shaft and bolted in, and then everything gets entombed in the concrete of the pile cap. And so one of the things that kind of can come up is how much embedment do you need? And Chance typically states that they want sufficient embedment for fixity, and that is typically 7.5 inches minimum from bottom of footing is what they state in the design manual. And if it needs to be less than that, we can design it as a pinned condition, and it'll reduce some of the capacities that are stated in the manual, but we can definitely help out with that. So then retrofit termination, this is just one of the two of the styles that are offered. We have a few others, and basically this termination, what it's trying to do is marry up the pile system with an existing structure. And so like I kind of alluded to before, the foundation gets chipped away up to the stem wall or up to the column, and that L-shaped seat goes under the stem wall of the footing to reduce eccentricity. And then there's a slight amount of quote unquote lifting pressure to engage the pile with the soils at depth. And it's not really a lifting. For the majority of piles, you're not lifting, you're just lifting enough to create enough strain to engage the loads. And so there's, you know, different styles, like I said in the design manual, that are more beneficial to use in certain scenarios than others. And if you have a specific project need, then we can help you with that. So the shaft is the part that transmits both the torque and the loads throughout the design life of the project. And we have basically two main options for shaft, which is the square shaft and the round shaft. And the square shaft is probably our most common, most efficient pile per load. And it is good, and it's great for transmitting loads through stiff to medium dense materials, and it's got great penetration. Sometimes though, you have to, you know, worry about things like lateral loads or having, you know, a relatively thick layer of softer soils can create a buckling concern, as defined in the chance manual, of like blow counts less than 4 for about, you know, over 5 feet generally as a rule of thumb. And so when you have these scenarios, you might have to switch to an alternative. But if you don't have those scenarios, square shaft is typically should be your first choice for the most efficient type of pile. And so the naming convention for square shaft for our products breaks down as a 2-letter designation SS, square shaft, and then 1 to 3 numbers, which represents the square dimension. And the weird one is SS5 versus SS150. Both of them are 1.5 inches by 1.5 inches. The only difference is it's a different grade of steel for the SS150. And so it's able to handle a bit more torque and a bit more vertical load. And so the SS5 is a little bit weaker and the SS150 is a little bit stronger. And all of the ratings are here. So you have your torque ratings as well as your uplift compression capacity limits on that right side. Those are the ultimate capacities of the bar. I will get into the torque ratings calculations in a little bit, but basically all of these have a K sub T of 10. So then our second flavor is round shaft, and this is the shaft you would choose if you had lateral loads or an unbraced length concern. Round shaft is a little less efficient with its torque to capacity ratios, has a little bit more problem with penetrating into denser materials, and it definitely becomes a bit heavier, especially as you go up larger pile sizes and larger lengths. But I'll talk about how we can kind of mitigate some of these concerns as well with our special pile configurations. So the naming convention for these is the first 2 letters is RS for round shaft. Then the next 4 numbers is the outside diameter in inches. So 2875 is an outside diameter shaft of 2.875 inches. And then there's a period followed by another 3 numbers. And those 3 numbers are the wall thickness. So it's the first line is a 2875 with a 0.203 inch wall thickness. And the more wall thickness you have, the more it'll resist. We also have a high capacity pile limited service pipe, which has a higher steel strength, and it's able to achieve quite a bit more torque. So it can be a better alternative than the 3.5 inch material for similar engineering properties for a cheaper price. So this table is similar to the square shaft table. It has the torque ratings and the ultimate compression capacity limits for each of the pile shafts. And you would just marry that up with whatever your design nodes are with a factor safety of 2. And one thing that's different between square shaft and round shaft is it has a different torque to capacity ratio. And it's a variable torque to capacity ratio depending on the diameter. And I'll get into that in a little bit as well. So we also have some special configurations and components. This is a list of the main ones that we encounter. So you have a helical pull down, which is basically a grouted helical. We have a combo round shaft, square shaft pier that we have an adapter for. And drive cast displacement piles is a large grout diameter displacement pile option that we offer. Rocket lead sections is a special type of lead section that has some carbide cutters and different things for it that I'll talk about, and then walkway brackets. So pull down, helical micropile, grouted helical, it's all the same thing. Basically, it is the same helical pile, you just pull down a grout column with it. And so that grout column allows you to develop skin friction along with end bearing in your lead flights. And you're able to achieve higher structural capacities and geotechnical capacities than just the bare bar itself. We also have options for pulling down casing with the grout column to be able to resist flexural moments up near the upper depths of the pile. So this is a very common solution that we have when we don't have stiff enough soils for end bearing in our flights. We can pick up quite a bit of skin friction with these. One thing to note is tension structural capacity is still going to be limited by your steel. So then the second special type of pile configuration that we have is the combo round shaft square shaft. And basically, if you took the advantages of square shaft and married it with the advantages of round shaft, that's what this pile is doing. So you're able to kind of tackle that lateral load or buckling concern in the upper depths, and then you're transitioning to square shaft, which is just a more cost-effective pile in itself. So, and the bolt goes through both shafts in the coupler, so you can also transfer uplift through this. Drive cast is our displacement pile option, and basically this is a large diameter between 2875 and I think up to like 6-inch pipe shaft with up to like 24-inch diameter grout column displaced. And this pile goes into the ground, and it's basically creating a large diameter grout column, and then the steel of the helical becomes the reinforcing for the pile itself. So it's a one-pass installation. You get down to the bottom and you're done, and you put a pile cap on top, and it gets entombed in a pile cap as well. So this is typically used in softer profiles because you're gaining that skin friction with depth, and typically limits 40 feet depth. They just start to torque up at that point, but you can achieve some different lengths if you do a little pre-drilling, if that's a necessity, and can achieve very large capacities, 170 to 300 kips of allowable load, and it'll obviously depend on your soils. So then another option we have is the rocket lead section, and this is a lead section that has a carbide tip cutter on the very tip. It's got thicker helical flight sections with heavier welding, and basically this can be used in shales and cobbles and gravels when you have lenses that you have to penetrate through, and you don't want to have to worry about torquing up or chattering. Basically, it'll help penetrate through those materials a lot more easily. Then we have walkway brackets and other terminations. You can see on the left, we have an all thread adapter. So you could, transition this into some sort of a plate that you can put at any elevation or something of that nature. We have a retrofit porch bracket, a slab bracket, a walkway bracket on the bottom right for grabbing onto the beams at the bottom of the walkway. And then up at the top right, you can see we have shackles, eyelets, thimble eyes, triple eyes, basically getting cable connection to our piles. We're able to get that. So, and if you have questions on that, or if you're looking through the product catalog and you have a specific need for a project, we have Sam and I have multiple years of experience, but we also have access to Chance's engineering staff who's had 30 plus years of experience across a number of people. So if you have a specific project, termination need or really anything, we have quite a bit of a cloud in the industry. So you have any questions on any of that at this point?
I don't think so.
Good. Hopefully that means I'm doing a good job.
We'll get there. Yep.
All right, so now I'm going to go through the system installation, and before I get into the actual installation, I'm going to talk about the different methods of installation. So the first type is hand installation. This is usually used in basements or hard to access areas, and it basically consists of a drive head with a torque bar that has a spider valve or a pressure valve that feeds pressure from an external hydraulic power unit that has hoses that connect everything together. And basically that you can take that, hose it in somewhere that's hard to access, and torque your helical in a hard to access area. So we currently carry two options: a 2.5 kip foot drive head with an 8-foot aluminum torque bar, and then we also have access to a 5 kip foot drive head, and the torque bar for that needs to be fabricated by an external vendor. But I don't know, Bill, if you have any other hand installation options at this point, but I think we have access to a number of vendors and we might be able to.
Yeah, and did you say the torque indicator needs to be fabricated? So the manufacturer.
No, I was talking about the drive heads, the torque bar.
Yeah, so the torque bar is provided by the manufacturer now. So.
Oh, okay.
But
so that's cheap.
And there's also a 7K, and there's a plethora of options, sizes, and torque.
Yeah. So if you have a specific need, but if the contractor has a specific need, we can help them out with that. So then for the second style of installation is an excavator mounted installation equipment, and basically the drive head gets mounted onto the arm of the excavator, or some sort of a equipment that has hydraulic power, or you can still run this off of an external power pack as well. And basically this consists of the drive tools, a torque indicator, and bar adapters. And Bill can attest to any other flavors or options that we have. But I don't think we need to know that for now. So the general drill setup, the drill string for the excavator mounted setup is the excavator's at the top and it gets pinned into the drive head in some way. And there could be some sort of adapter that goes between the excavator to mount to the drive head. And there's multiple configurations of that, but for now I'll skip that. So you have your drive head. Your drive head comes out as a Kelly bar. So you have a Kelly bar adapter that has a bolt circle that mounts to a torque monitor, and then that torque monitor has female bolt holes that you can put a drive tool onto. So basically that drive head is the drill, and it's applying the rotary torque to everything. It requires pressure and flow from an external source of some sort, and you have to have sufficient pressure and flow to run the drive head to the torque that it's rated for. Otherwise, you lose power. Then that Kelly bar adapter is just transforming it into that bolt hole pattern. And then the torque monitor is basically an inline measurement of the torque through the system. And there are other methods of measuring your torque, which is the most important thing to measure while you're installing these piles. But we prefer this digital torque monitor because it's calibrated, it's internal to the string, and they just have shown that they provide a much more accurate representation of the torque through the system while you're installing. So we recommend this style. And then you have your drive tool that transforms that bolt pattern into a shaft specific coupling. And so this would need to be matched up with the bar type that's being installed for the project. Okay, so now I'm going to go through a number of slides that represent the installation procedure for a retrofit, and then I'm going to go through the procedure for a new construction, which is mostly the same. But so with an existing structure, for this case, we're going to consider a building. You'd start with your stem wall, you'd start with your footing, and you're going to excavate down and partially demolish the footing up to the stem wall just to get closer to the load. And it's really important that this face is very smooth and angled at a 90-degree angle under the building so that we can have the most contact with the retrofit bracket with the structure. And it's important to have the right tools for the job and making sure that you're making that the most smooth and the most neat that you can make it. So once we have all that excavated and partially demolished, you bring your lead section up into the hole and you kind of angle it back to be able to get the flight sections under the footing, and you connect your drill string to the lead section and you apply crowd and torque to advance the lead section most of the way into the ground. And when it's most of the way into the ground, then you're going to disconnect the drill string from the lead section, and then you're going to add an extension, and then you're going to reconnect your drill string up to that extension, and then you're going to do the same thing. And so you're going to keep doing that, monitoring torque until you get to a depth or a torque that's required for the project. And then at that point, once you've achieved that torque, then you're able to terminate your pile. And the first step in terminating your pile is going to be cutting off extra shaft. And then you add your lifting setup. So this lifting setup is the retrofit bracket and a lifting ram and a lifting bracket. And basically you are pushing down on the pile while lifting up the building. And while everything is engaged, there are some set nuts that you screw down, and it basically reduces the length that you set the pile back down on. And so you're basically lifting the structure and locking that off. And you're doing it typically just enough to engage the structure. And then once you're at that point, then your element is installed and finished, and then you can put your backfill back around it. So then for a new construction, it's pretty much the same thing. You're going to put your lead section with your drill string into the hole. You're going to apply crowd and torque. You're going to disconnect everything, add an extension. You're going to do that again, advance it with crowd and torque again. And then once you get to your torque that allows you to terminate your pile, then you cut off excess shaft. That's probably going to be determined by the surveyor to be within the right level of the pile cap. You set your appropriate termination on top, putting your bolts in if uplift is required, and then everything gets cast into the footing for the building or pile cap for your structure. So some of the main talking points for helicals is, it's really important to screw these into the ground instead of drilling. So you don't want a lot of material coming up out of the hole. If you are displacing the materials out of the hole, that is creating a void, and the pile won't be secure. So that's really important. And coinciding with that, you gotta have enough crowd to push down on the pile while you're advancing it. Because sometimes if you don't have enough, you won't get enough penetration into the soils, and you will start to drill the material out. And so it's important to have maybe a come along if you're doing a hand install, and be ratcheting it down while you're spinning to really get it engaged with the soil. Or if you're doing an excavator mounted setup, maybe it's just necessary to have heavier equipment to give it enough crowd to be able to push down on the pile enough. So the rate of spinning is you want one helix pitch, which is like 6 inches of penetration per revolution. And if you're sitting in the same spot and turning, basically that's spin out. That's going to be constantly displacing the soils above the helicals, and it's going to create a bad condition for the pile to be able to transfer the loads. And if you have load testing, we recommend that you complete your load testing and get to a pass-fail before you start installing a large number of the piles. We've had people, try to, do it all at the same time, and they get a load test that doesn't pass, and then they have a lot of piles to figure out what they're going to do with, which is not it doesn't do any good for anybody. So it's definitely recommended to do that load test first. So one of the more common special scenario piles that we come across is the grouted helical. So I'm also going to go through a quick demonstration of the installation of that. And basically, like I said before, a grouted helical is the same thing as a regular helical. So it's got shaft, plates, and a termination. The only difference is you're going to pull down a grout column by gravity as you advance the pile. And so you would start with your lead section like normal, and you'd spin that into the ground with a little bit of shaft remaining above the ground. Then you're going to add a reservoir. You're going to add what's called a lead displacement plate, which is a plate that has paddles on it. And that's going to be on your lead section. Then you'll add your extension section above that. And then you have your grout reservoir, like I said. And you probably need to bury that a little bit so that grout doesn't run out the bottom. So basically, while you are applying crowd and torque, that lead plate, displacement plate, is creating a annulus in the soil that is going to be gravity fed with grout, and the cuttings of it will be floating up out of the grout as well. And you're just keeping that filled the entire time while you advance the pile. And so we also have extensions that we'll add, and we have extension displacement plates that kind of make sure that the hole stays open, and it has holes in the extension plate so that grout can flow through and connect between the two. So it's just important to keep advancing, apply crowd and torque, keep filling that grout bath up so that the grout keeps pulling down with the annulus being created. And then once you get to this one's a little special. So you get to a torque as well as a length that you initially designed for, and then you can terminate it. And so once you get to that point, you cut off your pile at the level it needs to be cut off at, put on your pile cap termination, and then everything gets cast into the footing. And so, like I said before, it's all the same components with your lead sections, extensions, and termination. You're just adding a lead displacement plate and an extension displacement plate. So something that's come up before that I think is important to communicate is there are varying degrees of lateral resistance, and I've kind of ranked them. and it says no lateral load. The square shafts can resist some lateral load, but it's quite small. And most of the time when there's a lateral load on a project, you're not considering square shaft very quickly. So for some lateral load, you know, maybe a few kips lateral load, you can get away with round shaft, combo pier. So you got that round shaft up top down to a square shaft at the bottom, or a grouted helical can resist some. And then if you want to get the most lateral load, you'd be going with a cased grouted helical more than likely. So these are say that again.
What's it cased with?
So you just advance it with casing that is like, you know, ASTM A50 or 500 pipe.
Okay. So steel pipe though.
Say that again.
Steel pipe.
Yeah, steel pipe. Yep.
Is that usually galvanized?
I think we get that galvanized, or it comes galvanized. We can help either way. Most of the time our partners are finding that.
Yeah.
And then another thing that isn't on this slide actually is if you had a couple, you know, if you have a known direction of your lateral loading, you can put battered piles parallel with that load to resist it. And if you have your battered piles to resist that load and you're holding that pile cap static, then you don't have to worry about the vertical piles, you know, reacting. Because typically what happens is if you install these piles to the torque correlated capacity, so you're getting into something dense, we typically see about a 1/4 inch to a 1/2 inch deflection from our piles in that case. So you're holding the tops of your piles to a 1/2 inch deflection for your vertical ones if you've got battered ones intermingled with it, if that makes sense.
Mm-hmm.
So did you have any questions on the installation?
I don't think so.
Okay. So then we'll go into the design. So the design workflow that we see for most projects is somebody determines an estimated load per length of footing. So a structural engineer is going to evaluate the existing structure, or they're taking their new structure and applying all the load combinations and figuring out, okay, this is a column load. I think I can get away with a number of piles. And so they'll space, you know, point loads for our piles to resist that load that they came up with. And then if you take that load per length of footing or the column load divided by the number of piers, that's the required load per column, per pier. And then somebody maybe figures out, okay, geotechnically this doesn't make sense, and that spacing or quantity of piers can be revised to make it geotechnically work as well. I feel like that's kind of a common thing that we help with is somebody, you know, will look through the design manual and they'll see the structural ratings of the piles and say, okay, well, you know, we can get away with 150 kip pile. And then they get to the geotechnical design and realize, oh, the soils are really only ever good for 70 kips. So we got to switch up the pile. So that's one thing that I really enjoy doing, is trying to figure out what's the most efficient number of piles geotechnically that also works structurally. And then once you have your design, you install your piles until the planned torque and depth if it's a grouted helical, and you terminate it. And you can also do load tests to verify the strengths of the system, typically with the torque correlated capacity. So if you're terminating it based on torque, there's like a 95% confidence that your pile is going to perform at or greater than the capacity stated by the case of T value. So geotechnical strength of the system is determined by the ultimate bearing capacity of the soils at each plate. And that can be verified through load testing, like I said, or the torque correlation factor, which is an empirical relationship. And I'll have that in a couple slides, I believe. So then a maximum load per pier should be estimated, like I said, based on the type of structure, but it also needs to take into account the condition of the structure. So if it's new retrofit, like new retrofit or old retrofit, and the spacing of the elements. So if you have relatively weak in the sense of spanning flexural strength of a pile cap for like a strip footing, you might have to space your elements closer because the pile cap or grade beam can't span the loads and lengths that are planned. And throughout installation, the torque needs to be monitored no matter what. So you said that you have the Chance Technical Design Manual, and if you have any issues with that, let me know. But we also have an online software called Helical, and basically Helical is a way you can go into and put in a soil profile and try out a number of different lead sections and lengths for piles and figure out what is the ultimate capacities I could use for a pile. So it helps establish a design for estimating purposes of, you know, this pile should work in this soil profile, and here's the calculation that represents it. And basically, Helical is going through and calculating the bearing capacity of the plates with, you know, a number of depth iterations and coming up with, you know, here's the point at which the pile should work. And Chance has a number of online tutorials. I also plan at some point to create a shortened version of the tutorials to kind of give a good rundown of the workflow of starting a project to ending it. They have a lot of parts and pieces for their tutorial, but it's pretty user friendly and pretty intuitive to use if you used any other software packages at all. So then the Chance Technical Design Manual has the engineering properties for all the products that Chance carries, you know, all the section modulus areas and corroded areas and stuff like that. And that it'd be provided on a per shaft basis for the helicals as well as the resistance piers, push piers. And then also in the Chance manual, there are a couple sections that I think are pretty useful for engineers. Section 3 is a product feasibility, so it kind of gives you the overall idea of if I have a soil profile, I can have a good intuition that helicals are going to work because it's a soft profile forever versus Atlas resistance piers. It's an end bearing element on a hard end bearing zone, so you got to have something hard, and you can have a good idea of when helicals are going to work or when they're not going to work. Section 5 is the design methodology, and that kind of walks through all of the geotechnical and structural principles that should be used for engineering design. And then Section 8 goes through a number of different design examples that are worked out, which is very useful to see all of the parts and pieces that should be considered from an engineering basis. And then Appendix C is a basic guideline for designers, and it's almost like a set of specifications. And we also have standard specifications that can be provided and cut to be specific for the project that's being worked on. And I talked about the tutorials. So now I'm going to talk about the torque correlated installation and the termination criteria for that. So a lot of times that's one of the benefits of helicals is you have a pile that you're going to install and you don't necessarily need to do a load test. And the reason for that is statistically, empirically, the chances, you know, been involved in by selling their equipment and selling their product, thousands and thousands of projects across the world. And basically they've developed an empirical relationship between the pile's capacity and the torque. And I think that an intuitive way of thinking about it is installing a screw into wood. And if you think about installing a screw into oak and then pine, if you did that, it would be harder to torque your screw into hard oak than it would be to soft pine. And then following that, once I have both the screws installed, it'd be way harder to push or pull on that hard oak screw than it would be the soft pine screw. And helical piles act the same way. If you have hard soil versus soft soil, it's obviously going to be harder to screw into hard soil than it would be soft soil. And thereby it would also probably, since it's harder soil, react better to a load applied to it and transferred through the flights. So this relationship is the pile capacity is equal to the measured torque times the K sub T value, the empirical torque correlation factor. And so the K sub T is a number that they've statistically decided is the ratio of torque to capacity that makes sense. And for square shaft, I'll get into the why in a few slides, but for square shaft, the K sub T is always 10. And for round shaft, it varies based on the outside diameter, and it gets less of a relationship between torque and pile capacity with the larger diameter you have. Another important thing is this relationship is based on the measured torque, and it is possible geotechnically to have more capacity with depth by having a material below your pile that is way stronger than the material you've gone through at this point. So if it's like a really dense sand that you kind of terminate in, the pressure bulbs at the bottom of your lead section are going to engage with that denser material, and it'll allow you to have more bearing capacity. And you can, they are self-testing is what we call it, where, if you're monitoring the torque, it's typically, depending on the engineer record, acceptable to use that torque and use that torque correlation factor to allow for pile acceptance. But that'd be dependent on the engineering team's level of risk aversion. So another way that I like to display this equation is, and it's useful for contractors, is, what torque do I need to get to for a load? And so if you just rearrange the equation for required torque, it equals the pile capacity over that K sub T. So somebody starts out by saying, okay, I got a 20,000 pound pile I need. What torque do I need to achieve using an SS5? You take that 20,000 pounds of pile resistance you need and divide it by 10. And so the required torque would be 2,000 foot-pounds, or 2 kip feet. So then for the same load scenario, if we were to say, maybe there's some lateral load, or there's a buckling concern up top, and we have to switch to a round shaft, and say it's a 3.5 inch round shaft with the same load, what torque would I need? And so you basically take that same load and divide it by 7, which is the K sub T for a 3.5 inch round shaft, and that says that you need a required torque of about 2850 foot-pounds. And so design example 1 with square shaft required 2,000 foot-pounds, whereas design example 2 required 2850 foot-pounds. And so that discrepancy happens because of the K sub T values. And that discrepancy really happens because there's a number of things generating torque while you're installing the pile. And so you have torque from the lead section, and that's pretty much going to be the same whether you have round shaft or square shaft. But then you also have torque or drag from the pile shaft itself. And if you look at the profile or the cross section of a round shaft, the hole that it's creating is in constant contact with that full circular profile. versus a square shaft, since it doesn't have a continuous diameter because it is square, it'll have 4 points of contact as you install it. So you're reducing that contact pressure between the shaft and the soil the entire time you're installing. And those 4 points of contacts happen whether you have 2-inch by 2-inch square bar or 1.5-inch by 1.5-inch square bar. It's still just 4 points of contact. And that's why the square shaft has a case of T of 10 for all the square shaft sizes. And that's why it gets smaller with bigger diameters of round shaft, because you have more surface area on the outside of your round shaft the bigger the shaft is. So I kind of talked about this a little bit before. The what is Helical really doing? Basically, you know, it's you put in a soil profile, and based on your depths and size of your plates, you can calculate the ultimate bearing capacity for a bunch of different depths, and you can figure out what depth does this pile configuration give me the capacity I need. And that needs to happen both geotechnically and structurally. So it's taken all of these things into account and spitting out an output and saying, this is how the pile is going to perform, and this is the resistance you're going to be able to achieve within a specific soil profile with a specific lead section. And it'll do things like, you know, limit the pile based on the bolts. It'll limit the pile based on the welds. It'll limit the pile based on, you know, a lot of structural things, to where you don't have to worry about, you know, overstressing plates or doing this. It limits a lot of that to take that concern out. So then deflection, I talked about before, typically 1/4 inch to 1/2 inch deflections at service load, design load level, and then and it'll depend on the material you torque into. You know, if you're kind of coming down and bearing on rock, it's just going to be a PL over AE, you know, calculation. You're not going to displace it at the tip. You're going to displace it through compressing your pile shaft itself. So we talked about before, the Chance Design Manual has section 8, which goes through design examples for helicals that are worked out. And then some information that's always needed to estimate a quote for a helical project is, this is basically what we try to get our sales guys to get to, is we want to know, you know, quantity of elements. We want to know, you know, what are the loads to give us the shaft type, the pile length, and the lead section configuration. We need to know if it's new construction or retrofit. We also need to know the soils to be able to determine some of those things as well. So soils report, things like that. So geotechnical report giving us not just like a description of the soils. It needs to have some sort of engineering in situ shear strength data, or data we can correlate to that. So blow counts, unconfines. I don't really like basing anything off of pocket pens. That's not what I like to do. I worked in the geotechnical industry for 8 years, so I feel like I'm a little more snobby about some of that than other people. But I also know how thin those budgets are. So some sort of plan layout with a detail of helical elements can be helpful. Design loads, and then helical specifications. So that ended 5 minutes later than I normally do, but this is a breakdown of the main takeaways. Just want to see, do you have any questions at this point, or do you want to go into the project that you had that we were going to talk about?
You know, I think it'll be easier to correlate questions if I pull up the project.
Sure.
So
You want me to go ahead and cancel the recording at this point?
yeah, that'd be fine.